All right, so I'm going to go ahead and go through number 23 from the Physics 1 textbook in Chapter 5. And this one, it starts out by saying that in order for a car to maintain a constant speed, the force from drag and the force from friction need to equal the force from the engine, or the applied force. And the reason for that is because if we want the sum of the forces to equal 0 because we want acceleration to equal 0, the forces pointing in that direction need to equal the forces pointing in that direction, right? So these are our two forces that work against us, and this is the force that works for us. And so if we don't want to be speeding up or slowing down, if we want an acceleration of 0, then the net force in our system needs to be 0, which means that these need to equal these. And then we'll just keep moving at whatever speed we were moving at. So you actually don't have to figure anything out with this in the problem, because all it's asking you for here is it says, what are the magnitude of the drag forces at 70 kilometers per hour and 100 kilometers per hour for a Toyota Camry? And then it says that the drag area is 0.7 meters squared. So if we write out our drag formula, 1/2 times the drag coefficient times the density of the fluid we're traveling through times the area times the velocity squared. So if we look at this, our C value we can look up in the book, and we find out that it's 0.28. Our density we can look up in the book, or you can look up online, and you would get something close to, depending on where you get it from, 1.21 kilograms per meters cubed. Our area, it tells us in the problem, is 0.70 meters cubed, squared, and then the velocity is equal to, for the first part, 70 kilometers per hour, and for the second part, velocity equals 100 kilometers per hour. Okay, so now the first thing we want to do is, these can't be in kilometers per hour. We need to make those into meters per second. So we can say 70 kilometers per hour times 1,000 meters in every 1 kilometer times 3,600 seconds for every 1 hour. So now I have kilometers on the top and the bottom, which are going to cancel each other out. I have hours on the top and the bottom, which are going to cancel each other out. So for this one, I'm going to get 70 times 1,000 divided by 3,600, and that gives me 19.4 meters per second. And then I'm just going to go ahead and change this to 100 for simplicity reasons, and do the same thing. 100 times 1,000 divided by 3,600 is 27.8 meters per second. So this is going to be 19.4 meters per second and 27.8 meters per second. Okay. So now we can plug all this stuff in. So the drag force is going to be 1/2 times 0.28 times 1.21 kilograms per meters cubed times 0.70 meters squared times 19.4 meters per second squared. Okay, so we figure out this whole thing. I get 44.6. And that is going to be in newtons. And then for the next one, it's going to be 1/2 times 0.28 times 1.21 kilograms per meters cubed times 0.70 meters squared times 27.8 meters per second squared. Okay, so 1/2 times 0.28 times 1.21 times 0.7 times 27.8 squared equals 91.6. Okay, and I get slightly different numbers than they did, it looks like, but I'm seeing now that they did this out to 4 sig figs and I only did it out to 3, so that's probably what made those tiny differences, and that's nothing to worry about. So I am sticking with my answers. And then for B, we're going to do the same thing, but with a Hummer. So the only thing that is going to change is going to be our area. So let's just write out all of our stuff. So our drag coefficient is going to change, and that becomes, wait, our drag coefficient doesn't change. Yes, it does change. It becomes 0.64. Sorry about that. And then our density becomes 1.21 kilograms per meters cubed because we're still in air. Our area changes and becomes, they give us that in the problem, 2.44 meters squared. And then our velocities, those don't change, right? Yeah, no, it's asking us for the same thing, 70 kilometers per hour and 100 kilometers per hour. So we already know that that's going to be 19.4 meters per second and 27.8 meters per second. Okay, so we can figure out our first one at 19.4. So that's going to be 1/2 times 0.64 times 1.21 kilograms per meters cubed times 0.70 meters squared times 19.4 meters per second squared equals, and I'll just write out this one as well, and then I can just calculate them all. So this is going to be all the same until the very end. Okay. It's really hard to, let me just scoot this up. There we go. So I've got 1/2 times 0.64 times 1.21 times 0.7 times 19.4 squared. And that equals 102 newtons. And then we have 1/2 times 0.64 times 1.21 times 0.7 times 27.8. 209 newtons. So this is why you're going to get such better fuel efficiency for these two cars. Because this is so much more drag than the Toyota Camry going at the same speed. So the fact that it has this bigger area and so much more drag is going to play such a big role in the way that the car is able to move through the air. So that's what happens there, and that's why we like to have aerodynamic cars that are a little bit smaller if we want to maximize our fuel efficiency. If you're driving a Hummer, you're probably not trying to minimize your fuel efficiency, but if you are trying to, maximize your fuel efficiency, if you are trying to do that, then don't buy a Hummer. All right.